Welcome, my name is Dirk Drees and I'm here standing in front of one of our tribological testing laboratories in Belgium, where we address a lot of different practical issues related to tribology for industry. Let's have a look around.
From my side, I would also like to welcome you to our webinar on Falex Laboratories Testing Services, Solutions for Success. My name is Emmanuel Georgiou and I'm working as a project manager at Falex Tribology in Belgium, and I'm responsible for R&D and customized test services. Hope that you enjoy this webinar.
The main goal of this webinar is to draw your attention to the complexity of tribology and to the need of having reliable and relevant test methods where you can evaluate tribological phenomena that occur in the industrial field. As you can see from this slide, friction and wear can occur in different aspects of our life and in a wide variety of applications that can be quite diverse and ranging from biomedical application up to more demanding ones where a component have to operate under high temperatures like in the aeronautics, and therefore friction and wear are everywhere. That is the reason why there is such a high interest in this field. And just to understand the economical impact of it, you can see that on a yearly basis, billions of US dollars are spent to deal with tribological failures, such as lack of maintenance or lack of lubrication, and so on, whereas only in Europe and in the US, 1 to around 1.6 of their GDP is spent to deal with such type of tribological issues. What makes tribology so complicated and difficult to study is that it's a system property. This means that it depends on both the characteristics of the contacting materials. This means that it depends on their macrostructure, meaning grain size, existence of intermetallics, and so on. If they have some sort of flows, porosity, their intrinsic properties, and so on. Also, when we are referring to friction and wear, we should always have in mind that it depends on the contact conditions and on the environment under which these tests are being performed. Always, the hardest part is to try and match the actual conditions with those that occur in the lab test. The problem with that is that typically in in-field conditions, the components are operating under more complex conditions. Whereas when we go to a lab scale test, most of the contacts are simplified. This is done to save on cost and time, because time is money after all, but this typically results in a lack of correlations with the practice. As you can see in this graph, the more that we go from a complex in-field condition to a lab scale test, we save on cost and time, but at the same time, we lose correlation. That is why there should always be a balance between the correlation and, of course, cost and time of our testing. Typically with friction, things are a bit more easy as most of the tests take less time and typically they are more repeatable. But the main problem is when we are dealing with evaluation of wear, because in that case we have to perform long tests which typically have poor repeatability. So therefore we need to run a large number of tests. To deal with such type of industrial problems, we at Falex have developed a three-step process to deal with it. The first part is really to understand what is the industrial problem and what do I mean by that, why is the failure occurring, and what are the wear mechanisms that are taking place. After we understand how the failure takes place and what is the type of contact that we have in the field, is to try to find a test method that most precisely simulates this type of contact conditions. After we find this type of match, then we need to perform the test and we need to be sure that these tests are relevant, reliable, and very important, they should be repeatable. So what we are actually aiming for is those 3 R's: relevant, reliable, and repeatable. Even though if we have a procedure, what is also very important is to have the correct tools and of course to have the proper know-how to understand the phenomena that are taking place in our tribo contact. We personally believe in Falex that we have all of the above assets, and that is why we are a good partner in solving industrial tribological problems. To illustrate that, my colleague Dirk Tres will present 6 indicative examples where we worked closely with industrial partners to solve some of their issues.
The first example we're going to discuss has to do with measuring the anti-wear performance of hydraulic fluids. Now, hydraulic fluids are used in a lot of heavy equipment for power transmission. Fluids need to be pressurized by a pump, and a certain measure of anti-wear property of the hydraulic fluid is necessary to protect the pump. Now, the challenge is that there exists a component test for evaluating this, but this component test is quite expensive and time-consuming, and it provides little information on friction. So the starting point is that we have the Conestoga-Vickers vane pump test, a component test that is standardized, but that requires a lot of oil to be used, 5 gallons, or for the ISO test even more, and a long test duration. At the end of the test, we only measure wear loss. So our challenge is to look for a simulation of this test and accelerate the testing without actually changing the wear mechanism. And the way we do this is by using a set of dedicated test specimens that you can see in the right bottom corner here. These test specimens can be fitted in the Falex multi-specimen machine, and they are designed to recreate the contact conditions, a sliding line contact of a vane pump. These are then set up in the test machine. And of course, an oil reservoir is placed around this, and we use a recirculation of the oil to lubricate the contact. After a test, we have to evaluate the wear mechanism that has occurred on these vanes, and we have to verify that it's the same wear mechanism that is also happening in the component or in the vane pump test. And as we can compare these 2 scanning images, we can see that with the test method we have on the Vickers vane pump test or the test method we have on the multi-specimen test, we get similar wear mechanisms. The advantage of the screening test, of course, is that the duration is a lot shorter than on a vane pump test. We also need to use a lot less oil, and one test is also less costly in specimen costs. So we have a real advantage in testing faster and more efficiently. Of course, the test results have to correlate with reality. And this is something we have checked in an extensive comparative program. We have used 5 different hydraulic fluids and ran the Conestoga tests on them in-house. We also ran the multi-specimen simulation test on it. And we can find that the Vickers test and the multi-specimen test result in the same ranking of the fluids. The absolute values of the results don't match up precisely because, of course, we are doing a simulation. We have simplified the mechanism a little bit, and it would be too great to expect to have a perfect correlation. But we can rank the fluids very well, and we can therefore evaluate the effects of composition or test parameters on a fluid without having to go and run the complete component test. An interesting thing is also that we have discovered that our simulation test is quite sensitive to concentration of additives. So comparing 3 hydraulic fluids with 3 concentrations of additives added to it, 0 to up to 0.6%, which are quite small percentages, we can see that the weight loss in the simulation test is quite sensitive to these concentrations. In addition, we can measure the friction, and it's important to note that friction doesn't necessarily have to correlate with the wear, but it is interesting to see that different fluids generate a different friction response, so have a different energy loss in the contact. And this can also be relevant for the energy consumption of the system. In this example, we approached the challenge of simulating a deep drawing process on the laboratory scale. So deep drawing is a process that's been used extensively in the industry to form all kinds of components, going from large scale automotive to smaller components in consumer products. And the challenge exists that it is difficult to simulate the forming or the friction in the forming process on the lab scale. So a number of tests exist that are used in the industry and are deemed to be quite reliable. And an important one is a strip drawing method, in which large sheets of metal are being drawn through a set of tools, and the friction is measured. The downside of this methodology is that it requires quite heavy equipment, large sheets, and that you generally generate very little data throughout a test. The main advantage is that it correlates well with the industrial practice in the sense that coefficient of friction is generally seen to increase with working temperature. And we see this on this chart between 20 and 80 degrees Celsius, a significant enough increase of temperature. So a set of conventional lab tests were evaluated, Blint reciprocating test on the one hand, a roll slip mini traction test on the other hand. And we found very quickly that the temperature behavior is actually reverse or opposite of the industrial practice. So this setup does not correlate with reality, and therefore we have to find another approach. The approach we use is to use the multi-specimen machine with a special holder, a special adapter, that enables us to hold a piece of the actual sheet material in the holder that you see down here. And in this holder, we can pre-lubricate the sheet and we can heat the holder to different temperatures and then run a test that is at the same time a sliding and deformation test. A ball is used as a tool material, it's pressed into the sheet, and then it is started to move. And during this rotation, we are registering the frictional torque. Because the sheet is allowed to deform a little bit, it is a closer simulation of what happens in reality. After testing, we can plot the coefficient of friction, in this case as a function of different temperatures. And on the left-hand side, you see the results, and we see that the coefficient of friction in this simulation is indeed increasing with temperature, just as we have seen this in the strip drawing test. This methodology was developed with the support of a European research project named Aspect, and we'd like to acknowledge this project right here. It's really helped us to understand better the sliding and the friction mechanisms in deep drawing, and to find a methodology that would help people in this industry to more quickly evaluate the effects of lubricants, of temperatures, and of composition. In this example, we look more closely at a test method that evaluates the efficiency of cutting fluids for aluminium alloys. So aluminium alloys and in general lightweight alloys are of more and more interest in the industry. They can be used in vehicles, and it can really improve fuel efficiency. But the cutting fluids that are used in these processes have to be tailored a little bit to the alloys specifically. So our challenge is to modify a standard test method that will simulate more closely the materials involved in these cutting processes. Our reference method is a tapping torque method. The tapping torque methodology is using a real tapping tool and is performing a real cutting operation, as you can see it right here, and is therefore the closest simulation of cutting in practice. So with this method, we are evaluating three aqueous emulsions, lubricating emulsions in aluminium, and we will use that as the reference. The method that we want to improve and fine-tune is an existing test method. It's the ASTM D3233A, also known as the Falex spin and V-block machine, or sometimes known as the Falex test. It is a method that exists already for quite a long time and involves rotating a journal pin in between two V-blocks that are pressed against it with an increasing force or an increasing load. And the whole contact is lubricated by a small oil bath. And as we are increasing the load, we can monitor the torque that is performed on the pin. And we can also see at what load the system fails, at what load the lubricant can no longer sustain the load. So that is in a nutshell the ASTM method. But it uses steel specimens as the materials, and it is using a limited amount of oil. The modifications we have made to this methodology are, on one hand, let's reduce the sound there. On the one hand, to spray an aqueous emulsion directly in the contact, as you can see it here. And this has the advantage that we can use a larger volume that we are recirculating, and this keeps the temperature under control. It is also making it easier to clean the contact, to remove any chips that may be forming themselves. So all in all, it is a closer simulation to a real cutting process. We are also modifying the test specimens. Instead of steel specimens, we are using aluminum alloys as the pin material, and we can use hardened steel, or if you want to, we can use coated steels as the V-blocks to have a better representation of the tool. So in a nutshell, with the recirculating aqueous emulsion and measuring online friction force, we are hoping to get a bit closer to a simulation of a cutting operation. So what are typical results with this method? We are showing here the torque versus load curves for water without any lubricant in it, and a cutting fluid that is an aqueous emulsion that is made out of increasing percentages of cutting oil dissolved in water. As you can see in this graph, the purely water lubricated system breaks down fairly soon with quite light loads and has a high torque. The emulsions with 2.5 and 5% cutting fluid will survive to a higher load, and the emulsion with 10% cutting fluid to an even higher load. And also progressively, the torque, the frictional torque, is lower with an increasing amount of cutting fluid. How do these results compare to a real cutting operation in the microtap test? Well, these are the results of the tapping torque test with the same fluids. We see that the pure water indeed, as expected, gives the highest torque in a cutting operation. And then there is a gradual decrease of the torque with increasing percentage of cutting fluid in the emulsion. And when we plot our pin and V block results next to it, we see a quite good, almost perfect correlation between the torque in a pin and V block test and the torque in a cutting test. So the changes that we made, the modifications that we made to the standard method result in a closer simulation to real conditions of cutting with the aqueous emulsion that cools and cleans the contact and using the real alloys in the contact. And it also, very importantly, of course, correlates with the practice as is proven by the tapping torque results. In this example, we show in a nutshell how we are able to measure the tackiness of greases. So tackiness is a quality or a property of a grease which can be shortly described as its ability to form threads. And this can be a desirable or an undesirable quality. The thread formation certainly makes it possible for greases to lubricate moving contacts more easily. But today there is no real accurate measurement technique to measure this thread length and also the adhesion of greases on some materials. Historically, for evaluating the tackiness, this finger test is being used, where you place a volume of grease between your fingers and pull it apart, and you observe whether you are forming any threads and how long they are. The problem with this is that it is definitely a user-dependent test, and we can see here that it is also speed-dependent. When you separate your fingers faster, you tend to get longer threads. So all these factors together have inspired us to look for a quantitative method and to try to simulate this finger test, this indentation and retraction that you are doing, but to actually measure what is going on. And the approach that we have used is an indentation extraction experiment or an indentation retraction experiment. We've selected a copper ball as a probe, and we are going to push this copper ball into a volume of grease and then retract. And because we have a very sensitive and precise force sensor on this system, we can measure the forces involved with this experiment. And we can plot a force displacement curve like this, where we first get the indentation of the ball into the grease, which is generating a positive force on the sensor. And then we retract, and as the grease is pulling a little bit and adhering a little bit, we get a negative force, which we define as the pull-off force. And then we get the force that is gradually reducing. And during this time, we are forming the thread. So at the point where this force is crossing zero again, this is our definition for the thread length. Now we have this very precise measurement of displacement and force, so we can analyze curves like this and extract thread lengths and pull-off forces from some statistical experiments. When we do this, we can plot curves like this one, where we are showing the thread length that we have measured as a function of retraction speed in millimeters per second down here. And we are showing plots for a base grease without any tackifier added to it, and increasing percentages 0.5, 1, 2, and 4% of a certain tackifier. And we see indeed that the thread length is increasing with the amount of tackifier, which also corresponds with the subjective finger tests that we can show right here. So we have a correlation between the finger test and thread length measurement. We have a correlation between the thread length and an increasing amount of tackifier. So this tool gives us the possibility to actually measure thread lengths and compare them. We can, of course, do this for different greases. We can do it at different temperatures. We can do it under different circumstances. And so we have a tool in hand that quantifies this thread length. As we are doing this research, we have also discovered that while thread length is increasing with tackifier percentage, in this curve right here, this does not necessarily mean that the pull-off force is increasing gradually with tackifier percentage. And we see that in fact the pull-off force is decreasing with tachyfire, but also jumping up and down a little bit. There is no direct correlation between the pull-off force of a grease and its tackiness. Another surprising result we measured, in case of another grease with another tachyfire, adding 1% of tachyfire to the base grease, we get a little bit of an increase of the thread length. This is the performance of the base grease. But when we are adding 2% of tachyfire, we get a serious drop in the thread length. And you can also see in the finger test that the grease has actually completely changed its consistency. It's become much more of a gel, and it doesn't form any threads anymore. So the method also allows us to really quantify and repeatedly measure these kind of effects, these kind of maybe unexpected effects of tachyfire additives. So this first quantitative method for measuring the thread length of greases in pull-off experiments, it allows us to systematically research the effects of a lot of factors on tackiness. We can look at concentration of an additive, the influence of the base grease, the influence of retraction speeds and temperatures, and we can even change the probe, so we look at the influence of the metallurgy of the contacting materials. A lot of work has been done on this application already, and there is certainly a lot more details available in literature if you want to know more about this. In this example, we are looking at the abrasivity of clay slurries. And more specifically, we're looking at a specific problem in the brick production industry, where components are used in the processing equipment and they are suffering from quite severe abrasive wear by the clay that they are mixing and molding. And the challenge that this industry has is they have no consistent information about the wear resistance of different surface treatments or different alloys. So to address this problem, we are starting from an ASTM method. So we take our inspiration from an existing method, which is the ASTM G75. It's a slurry, sand slurry resistance test. And in this test, we are taking blocks of a material that we want to investigate. And these blocks are put in a moving arm, moving back and forth in a bath with a slurry. And the slurry creates an abrasive wear mechanism. After a number of time intervals, we are measuring the weight losses, and from these weight losses, we can distill what is called a SAR number, the slurry abrasivity response number. And the bottom line is that the lower the SAR number is, the more wear resistant your material is. This is what a test looks like in the case of sand slurry. So in the standard ASTM, a mixture is made with ASTM sand, and we are moving in this slurry. But to get closer to the industrial practice, we have modified the method and we have worked out a way to produce a consistent clay slurry. And you see that the clay slurry appears to be a bit finer. The test results show that when we are using a reference material, which is a hard tungsten carbide, in the standard methodology with the abrasive sand, we get a relatively high SAR number. With the clay slurry, we get a lower number. What's important is that these results are still fairly repeatable, just as they are with the sand. So we have a repeatable measurement method to look at the wear resistance of different materials in this clay slurry. Also important, of course, is that the wear mechanism that we are observing is the same as the mechanism that occurs in reality. And we can see in this clay slurry a mild abrasive wear process, which does correspond with the industrial practice. Now, we did a very large matrix of materials thanks to a European project that we were involved with, the ProSets project, that gave us access to a lot of different surface treatments. And in this graph, you see the evolution throughout the project. We have defined a reference material, which is the tungsten carbide, and a reference coating, which is a currently available hard chrome coating. And the SAR numbers in the clay slurry are around 50 or below that. And throughout the project, we have looked at this green family of coatings, which are thermal sprayed coatings, and this orange family of coatings, which are electrodeposited coatings. And then you can see that when we started with a non-optimized sprayed coating, the results were not very good, but as these coatings got optimized throughout the project, we reached similar results as with the reference material. This was not the case, however, with the electrodeposited coatings. Despite a lot of optimization steps, as we get further and further in the project, the coatings actually didn't get better, and we could never reach the same performance with electrodeposited coatings as we could with thermal spray coatings. The blue and the red were coatings that we were able to also acquire during this project. These were so-called promising coatings, but a very simple and effective screening test like this slurry test shows that this red family, PVD coatings, are certainly not wear resistant enough, and that the blue family here, which are laser cladded coatings, are also not good enough to replace the current reference materials. In this example, we are looking at simulating wear in a component on wind turbines. In wind turbines, it is very important to keep repair and maintenance costs low, to have a decent payback on the produced wind energy. And as these machines become bigger and bigger, the cost of wind energy per megawatt produced is starting to go down and become really competitive with other green methods. But there are a few key components that need to be kept well under control. And we are looking more specifically at the wear damage that is occurring on the slowest moving shaft in the gear system. Because it's slow motion, we're going to at first simulate this wear mechanism also under slow motion. And we are going to use a Falex block on ring test machine, because in this we can place a ring and rotate it slowly over block materials. The block materials can be a conforming block or a straight block, either creating an area contact or a line contact. And we can do this in an oil bath at a very low speed, as you can see it moving right here. With this test setup, we can vary the metal alloys, we can vary the alloy of the ring, and we can test a couple of different parameters that might be important, as well as the lubricated oil, of course. The key to the realistic simulation was to keep the rotation speed low. Of course, we tried in the initial stages of this project to accelerate the testing by accelerating the rotation speed, but we found that the wear rates at low rotation speed are a lot higher than if we go to higher rotation speed of, for instance, 72 RPM. The wear mechanism changes drastically over this range of speeds, and the only realistic wear mechanism is the one at low speed. The downside of this, of course, is that wear tests are taking quite a long time. We need to run for 48 up to 72 hours of wear tests. And this is, of course, making the test project progressing rather slowly. In principle, this could be accelerated by using a multi-station approach. And this is only showing a very small sneak preview of things that are going to come next at Falex Tribology. It's a multi-station setup where we can do the same slow moving rotation with the same conforming or straight blocks, but we can run a wear test at 10 locations, 10 stations at the same time. So in the same 48 to 72 hours, we're going to generate 10 times as much data points, and that will really accelerate this investigation. But as I said, this is future talk. At the moment, we are working still with the standard single station block on ring machine. And then using this machine, we can plot the wear rates for different materials. Here we are seeing the difference between aluminum tin straight blocks and bronze straight blocks, for instance. And you see that the bronze alloys are definitely wearing a lot slower than the aluminum alloys. And in this graph, we can see a distinction between using different oil formulations, always with the same straight blocks. And in this case, we're using, again, the bronze straight blocks. So the methodology gives us access and a possibility to screen different compositions of oils and alloys and to find the optimum cases for the wind turbine. Naturally, this is always complemented with a post-test analysis to confirm that we are still simulating the right wear mechanism. So the wear mechanisms we're seeing on block and ring under these low speed conditions are abrasive. And this is indeed correlating to what is seen in practice.
The reason we are so successful in solving industrial tribological issues is because we always try to be active in the field. We always try to expand our know-how, and we try to stay close to the needs of our partners. That we achieve by participating in committees such as ASTM, CEC, and IP, trying to develop new methods and new standards and modifying old ones to match the needs that we have nowadays in the industry. Also, we are a part of large associations such as the NLGI, ELGI, and of course, STLE. A large part of our success is being close to our partners, and that we achieve by performing bilateral collaborations or large-scale industrial projects such as the ones that you can see in this slide. The first one is Aspect project, where we have evaluated the frictional properties of oils which will be used in the automotive industry and also in the consumer goods field. In the second project, Process project, we had 4 actually different applications, and our aim was to rank coatings that should be used to replace hard chrome, because chrome 6 is now banned in Europe. The first application came from the automotive field, and it was for shock absorbers. The second one was for cutting tools in chainsaws. The third one was to replace coatings that are used for clay processing, and the last one was again from the forming industry for coatings that are used in rollers. In our third project, the Supersonic project, the idea was to develop new materials, nanostructured sprayed materials to be more specific, that are going to be used in biomedical application, and in particular for hip joints and for aeronautical applications. Finally, our goal is to disseminate our know-how, and that we do by participating and presenting in conferences, by organizing workshops, and by attending networking events to grow our partnership with more people, and by disseminating and presenting our new ideas in journals and technical magazines.
So that I remove my glasses so that I'm consistent.
Ready?
Yeah, I cannot even see it.
Action. So to sum up, what do our labs have to offer? Well, we have a lot of infrastructure in both our laboratories in the United States and in Belgium, with a lot of test equipment there. But even more important is the accumulated know-how that we have been gathering for the last several decades, and we are still developing new know-how in how to translate an industrial problem into a lab testing program. So we keep working together with our partners, also with industrial partners, on improving existing standards and making new procedures and new standards. And all this fits in the innovation tradition that we as Falex have had, and where we cooperate in European projects bilaterally with industrial partners towards new test equipment and new test methods.
We hope that in the near future you make our labs your lab. From the Falex Group, I hope that you enjoyed this webinar.